Okay, so what if I told you there's a way to write code that solves a problem by calling itself? It sounds kind of crazy, right? Like a paradox, a surefire recipe for an infinite loop. Well, this mind-bending concept is called recursion, and honestly, it's one of the most powerful and, I think, elegant tools in any programmer's toolkit.
And that brings us to the big question, the central mystery. If a function just keeps calling itself over and over, what on earth stops it from running forever? How do you keep the code from becoming this snake, just endlessly eating its own tail? Well, let's unravel that secret.
So yeah, let's start right there with that core challenge, a function that just calls itself again and again. I mean, that sounds like a recipe for disaster. It's pretty much a guaranteed computer crash. So how do we turn what looks like a bug into an incredibly powerful feature?
You know, the best way to think about it is like a set of those Russian nesting dolls. To understand the whole set, you open one doll, and what do you find inside? A slightly smaller but identical doll. And you keep doing this. You keep opening them until you get to that tiniest little doll that just can't be opened. That, in a nutshell, is recursion, solving a big problem by finding a smaller version of the exact same problem inside of it.
Okay, to really see this in action, we're going to use a classic mathematical example, the factorial. This is perfect because it'll help us build the logic of a recursive function, but more importantly, it's going to show us the exact flaw, that one little mistake that can send us spiraling into an infinite loop.
So, you probably remember from math class that 4 factorial is just 4 times 3 times 2 times 1. Simple enough. But here's the recursive insight. You have to look closer. See that 3 times 2 times 1 part? Wait a second. That's just 3 factorial. This is huge. It means we can redefine any factorial, let's call it n factorial, as just n multiplied by n minus 1 factorial. We've just defined the problem in terms of itself.
Let's actually trace this logic out. To solve fact of 4, our function needs the answer to fact of 3. Okay, well, to solve that, it needs fact of 2. This chain just keeps going down. Fact of 1 needs fact of 0. But what happens then? Following our rule, fact of 0 would try to call fact negative 1, which isn't even a thing. Our beautiful chain just broke. It really looks like we've created that infinite loop after all. Or have we? See, there's a crucial piece missing from our little definition. And this piece is the secret sauce that prevents the whole system from collapsing into an endless, looping nightmare. It is the escape hatch.
Think about it. Every recursive journey needs a destination. The function has to have a point where it stops breaking the problem down and just knows the answer. Without this stop sign built right into the code, it absolutely will run forever.
In programming, we call that stop sign the base case. It's the simplest possible version of the problem. It's so simple that the function doesn't need to call itself again. It just spits out a direct answer. And for factorials, the simplest case is 0 factorial, which, by mathematical definition, is just 1. That's it. That's our escape hatch.
So a complete, working recursive solution always needs 2 parts. First, you have the recursive case that keeps breaking the problem down into smaller pieces. And second, you have the base case that finally stops the chain. When you put those 2 together, you get a really powerful and totally finite process.
All right, now that we have both the engine and the brakes, let's replay our fact 4 calculation and see how this actually works from start to finish. It's pretty cool.
So here we go again. Fact 4 is called. It basically says, hey, I can't finish until I get the answer from fact 3. So fact 3 runs and it says, well, I need fact 2. This continues all the way down the line until fact 1 calls fact 0. And right there, bam. Fact 0 doesn't call anyone else. It hits our base case. It knows the answer is 1. And this is where the magic really happens. This is the second half of the process. Fact of 0 returns its value, 1, back up to fact of 1, which has been waiting patiently. Now fact of 1 can finally finish its job. It calculates 1 times 1 and returns 1. That result goes up to fact of 2, which calculates 2 times 1 and returns 2. You see? The answers are bubbling all the way back up the chain until the original call gets the final piece it was waiting for.
And finally, that result reaches the very top. Fact 4 gets the 6 it needed, calculates 4 times 6, and returns the final answer, 24. The chain is complete. No infinite loop.
Now, programmers choose this method not because it's always the fastest, but because for really complex branching problems, like, say, navigating a whole file system, the recursive code can be incredibly clean and so much easier to understand.
Now you might be thinking, okay, that's a neat trick for factorials, but is that all? No way. This pattern, a recursive case paired with a base case, is a fundamental problem-solving technique. Let's see it one more time with another super famous mathematical sequence.
The Fibonacci sequence, it starts with 1 and 1, and every number after that is something the sum of the two that came right before it. So 1 plus 1 is 2, then 1 plus 2 is 3, 2 plus 3 is 5, and it just keeps on going. It's another one of these patterns that seems to define itself.
And you guessed it, just like with factorials, we can define it with our two parts. For any number n that's 3 or bigger, the answer is just fib of n minus 1 plus fib of n minus 2. That's our recursive leap. And if n is 1 or 2, well, we just return 1. That's our base case. See the pattern?
So let's just formally name our two key players here. We've got the base case, that's our stop sign, and we have the recursive case. This is the engine, the part that makes the leap by calling itself on a smaller version of the problem. But a little pro tip here. While this Fibonacci code is beautifully simple, it's also really inefficient because it ends up recalculating the same values over and over again. This kind of highlights a key trade-off. Sometimes the most elegant code can lead to performance issues, or even a stack overflow error if that chain of calls gets way too deep.
So, there we have it. We've cracked the code. We now have the two essential ingredients that separate an elegant, beautiful recursive solution from a catastrophic computer-crashing infinite loop.
It really always comes down to just these two ingredients. You have the recursive case, which makes the leap, breaking the problem down. And you have the base case, which provides that all-important escape hatch. And like we saw, if you have the engine, but you forget the brakes, you are headed for a crash.
So, to leave you with a bit of a challenge, think about this puzzle. A frog can jump either 1 foot or 2 feet at a time. How many different paths can it possibly take to cross an 11-foot river? The solution isn't about just trying every combination. It's about thinking recursively. Try to identify those two key ingredients. What's the recursive case, and more importantly, what's the base case?